Thank you to my presentation. The title of my presentation is Topological Methods for Comparing Document Semantics. Give me a second. Okay. And motivation for that is because the document semantic comparison is one of the toughest tasks in the NLP natural language processing, and most of the relevant methods are based on the statistic and vector space model. But we know that the document semantics represented by both lexical and syntactical information. Lexical semantics is the word meaning, and syntactical semantics is the grammar or the language that how documents organized. So we propose a method that can unify both lexical and the syntactical meaning of the documents. So that's the idea how this works. So the mathematical basis. So everything is rely on the mathematicals. Two similar documents are share certain of the constituent components. Like a graph is a natural structure to illustrate the relationship between any two documents or objects. And the third one and the most one is the model has to be computable, right? So after we mathematical modeling this document comparison problem into a graph, this graph has to be computable. So that's the idea. So before I introduce my method, I have to introduce some basic concept about the topological graph theory. So the first concept is the abstract computational complex. So abstract computational complex is a set of composed of points, line segments, triangles, and their n-dimensional counterparts, or we call them simplex. So a p-simplex is a p-dimensional simplex. So for example, the right picture is a simplicial 3 complex, because the highest dimensional object in this picture is a bottom right pyramid. So it's a 3-dimensional object, and the rest of the object is a lower dimensional object, such as a facelet and a segment and points. And second concept is filtration. So filtration is the sequence of indexed sets attached to the abstract simplicial complex, so indicating the moment when this simplicial complex appear in the sequence or in the graph. The third one, the most important one, is topological persistence. So the topological persistence basically describes the holes in the geometric space from the algebraic perspective. So we use this topological persistence to quantify the features of the topological graph. So basically, this is the method or toolkit to quantify, to compute the features in this topological graph. Okay, so for example, we have this square at time 0, so vertices 1, 2, 3, and 4 appear. And also the edge 1 to 2, 2 to 3, 3 to 4, 4 to 1 appear at time 0. So this square appear at time 0. And at time 1, so another point or vertex 5 appear above this square. And in time 2, so edge 3 to 5 appear to connect this square and this point 5. And time 3, another edge 4 to 5 appear to connect the point 5 to the square. And at time 7, a face appear, a triangle face appears, 3, 4, 5 appears, cover this triangle frame 3, 4, and 5 at time 7. So how we use this persistence to quantify this one? So we use this persistence diagram, or we call them barcode. A barcode is a virtualization of the collection computed from the abstract simplicity complex. With filtrations, is called a persistent diagram. So like this example in this picture. So in dimensional 0, so in dimension 0, we basically describe the connected component. Like I said, so at time 0, so 4 vertices appear and 4 edges appear as well. So they formed a square. So at time 0, there's a line appear. Okay, so at time 1, so the vertices 5 appear. So there's another point above the square. So there's a second connect component appear. So we have a second alignment appear at time 1. But at time 2, the edges 3 to 5 appear to connect both the points and this square. So the second component disappear. Only one connected component left, which one is the first one, the first alignment, first assignment. So this so from this point to the end, there's no another connect component appear. So there's only one line left to the infinity. So that's why there's a barcode in dimensional 0 appear like this one. Okay, so in the dimensional 1 is an important dimensional because we use this one to describe holes. So if the hole appears, there will be a line. So if there are 2 holes appear, there will be 2 lines. So like this example. So so at beginning 0, we have a square appears, and the square frame form a hole. Right, there's a hole inside this frame. Okay, so this first line appear at time 0. But when at time 3, so there's when the edge 3 to 5 connect the vertices 5 and the square, there is another triangle frame appear. Frame formed by vertices 3, 4, and 5. So there's another line appear at time 3. But at time 7, so a fistlet or a face triangle 3, 4, 5 appear and cover the whole frame by formed by frame 3, 4, 5. So at time 7, the second hole disappear, but the square hole is keeping existing to the infinity. That's why this dimensional 1 diagram appear like this one. Okay, so the methodology. So how we transform this document, the semantic comparison problem into a topological graph. So first of all, we parse 2 documents into a bunch of parsing trees. Into a bunch of parsing trees. So like the graph shows, we have 2 documents, and for each sentence in documents, we parsing them using the constituency parsing tool into a bunch of parsing trees. But at this moment, there is no any connected component in this phase because all those are a bunch of trees or a forest. So we need to connect them together. So we connect the 2 similar words between the 2 documents, like this picture. So we have sentence 1 from document 1 and sentence 2 from document 2. Before the connection, there is no connection between these 2 documents, but we connect the similarity words, similar words between them, like A to A, B to B. So after this one, we formed a rectangle, and there's a hole appear inside this rectangle. So once we have a hole, we can use the persistent perceptron to compute this hole, right? Like I introduced. Okay, so this is after we connect the 2 documents, use similar words between the 2 sentences or 2 documents. So we extract out all the meaningful holes, like the second pictures. right? So how this hole appears. Please notice the second hole, the second picture, between the second picture is a C2, the circle 2. We treat them as a hole because in one-dimensional space, this distortion, we don't counter that. So this is basically its hole. And then we weight each hole by its filtration value. That's where the filtration value take apart. Right, so the filtration value. How we decide the filtration values? So basically, so each hole have two filtration values because they have, at least they have two edges to form a hole. So we use the similarity between this two words as this filtration values. Which value we use as this weight of this hole, not this edge? We use the minimum one. So like this one, so we have 1.0 similarity between this node and this node, and the 0.21 between this node and this node. So we use 0.21 as the weight of this hole, circle 1. So like this one. So after we weighted all the circles, we have this diagram or barcode pictures. Then we simply sum all the persistence as our final similarity score. We just simply sum together, sum this three barcodes, three lines. So that's how we modeling the document semantic comparison problem into topological graph theory. Okay, so the testing, the experimental. The dataset we used is provided by Dr. McReilly's. It's 50 documents selected from the Australian Broadcasting Corporation's news mail services. So each document length varies from the 51 to 126 words, and this 50 documents forms 1,225 two-document pairs. So each document pairs provide human judgments as a golden standard or a ground truth, and the judgment range from 1 to 5. So 1 means the two documents are dissimilar to each other or has minimum similar to each other, and 5 means that both documents are very similar to each other. So in this 2,225 datasets, we have 1,095 pairs with a score less than or equal to 2.5. So we mark them as a dissimilar group or G1, and 36 pairs in this corpus with a score greater or equal to 3.5. We mark them as a similar group or group 2. So we use some multiple safeguards and the widely used method as our comparison methods. And the evaluation metrics is the error rate. Okay. So the results of our method is like this table. So G1, G2 indicate the similar group and the similar group respectively. So in this chart, we can see that our method, TopSam, achieved the best in the G1 group with the dissimilar group. So error rate only 2.19%. But in the similar group, our result is not the best. We cannot beat the NLTK two keys, which is the old widely used two keys in Python. Because this error rate in the similar group, the error rate is also not the best. But you can see we beat all this rest of the method, like even for the Docker-to-Vect, which is based on the word-to-vect and also neural network architectures. And also other widely used methods such as text-to-vect using the Jarka similarity or cosine similarity or even the LSA. So all those methods we beat them, but not the NLTK methods. And the computational intervals of all methods are set to 95%. For this fit hyperparameters is the threshold of the lean similarity. So this fit means all the word similarities above this fit, above this theta, we add an edge between them. So which means if we set the fit t equal to 1.0, means only exactly the same word or exactly the synonym word are taken in count, are generate the edges between them. Okay, so this is the details results between them. So if we treat the dissimilar group as a positive and the similar group as a negative, we can compute the persistent recall and F1 score based on this settings. I can see in this dissimilar group, we do a very good job and we achieve the best precision recall and F1 score. As well as if we treat the similar group as the positive and the dissimilar group as the negative, we can also compute this persistent recall and the F1 score. But as I said, this we cannot beat the NLTK. NLTK is really good results. But we know the reason why this happened, why our results suffered in the similar group. It's because this we use a very old word similarity comparison method, like a lean. This lean is already 30 or 40 years old. We use it because it comes box with the word net. So we use them as a very first beginning our word similarity comparison method. Okay, so the conclusion is our method TopSem is a supervised model, so we don't need any training process before we use it. It's like the NLTK things. It's out of box. It's out of box tool. You can use directly, and it's a very unique and the very first method based on the topological graph theory. And I do some research. There's no other one to do this in such a way to use the topological graph theory to do the document semantic comparison. And it can unify both lexical and the syntactical semantics together, because we use the constituting parsing tree to present the syntactical semantics, and use the word similarity comparison to present the lexical meanings of the words. And also we use the topological persistence to quantify them together and give you a score to compute any two documents similarities. Okay, so feature work. So as we know why this result is not that good in the similarity group, and we use the word embeddings to replace the link, such as the word to vac or a glove, to replace this link as the word semantic models. So okay, so oh sorry. So this after we replace it with the word embedding method, actually the result is pretty good, and we can lower error rate under 1% for both groups. So after we just simply replace this link with the word embeddings, and we can achieve the best results, beat all this comparison results, the comparison method. So this is the first, but we cannot show you today because this is only very preliminary results by replacing this link with the word embeddings. And also you can replace it with any embedding you want. So right, there's a bunch of word embeddings, pre-trained models in the internet. You can replace it with any one you like, or based on your domain of your task. Okay, so the second feature work is adding weight on the syntactical edge. like this one. So right now we only have the weights on this between the terminal or the node to node, but we didn't take account about this constitution parsing trees. So in the future work, we plan to give some idea about this weighting for the constitution parsing tree, like this one. So between this node and this node, we have two nodes in between them. So this we should weaken their weights because compared to this one, this node and this node, only one node between them. So this will have a strong bonding, and this one has weaker bonding. So based on this one, we will give some weakening methods for the constitution parsing tree, not just the lexical edges, but also the syntactical edges. So that's another feature works. And also we want to add some pruning technique to prune some non-critical parts of the parsing tree to minimize the noise, because in the constitution parsing tree we have some meaningful phrases like noun phrases or verb phrases, and also some non-critical part or meaningless parts like the PP part, like the other parts, CP parts. So all those parts are just meaningless, just for the constitution parsing tree, just for the syntactical purpose or the grammar purpose. So we plan to adopt some pruning method to cut all those non-critical parts to make this toposem, our method, more robust.